Look at this tiny cylinder. It's a uranium pellet, about the size of a peanut. It looks completely ordinary. Yet inside this unassuming piece of metal is an energy density that defies common sense. This diagram illustrates exactly what that means. To match the energy output of this single tiny pellet, you would need to burn through 1,800 pounds of coal, or roughly 150 gallons of oil. For over a century after its discovery in 1789, scientists thought uranium was practically useless. That changed in 1896, when researchers noticed the rock emitted an invisible energy all on its own. Pioneers like Marie Curie dedicated their lives to mapping this strange new behavior, which they called radioactivity. By the 1930s, the pace of discovery accelerated sharply. James Chadwick discovered the neutron, a subatomic particle with no charge but immense force. Shortly after, scientists realized that firing these neutrons at uranium atoms actually caused them to split apart, releasing a staggering wave of heat. This sequence of discoveries proved that a mundane piece of Earth was actually a tightly locked cage holding an incredibly violent energy source. This chart shows the primary hurdle in actually harnessing that power. Natural uranium comes in two isotopes. A massive 99.3% of it is uranium-238, which is stable and largely useless for generating power. The highly reactive isotope they actually need, uranium-235, makes up a razor-thin 0.7% of the rock. If you want to build a reactor or a weapon, you have to physically isolate that microscopic sliver and artificially multiply its concentration. This mandatory refinement process is called enrichment. During World War II, the United States government launched the Manhattan Project to solve this exact bottleneck. Scientists like J. Robert Oppenheimer were tasked with brute forcing a way to separate these isotopes to construct a weapon of massive destruction. To achieve critical mass, the uranium had to be enriched to over 90% purity. The successful, forceful refinement of this material led directly to the atomic bombs dropped on Japan. Today, we use the exact same atomic reaction to generate civilian electricity. But to do it safely, humanity had to construct one of the most rigorously controlled, highly complex, and inherently dangerous manufacturing supply chains on Earth. The process begins deep underground. In places like Saskatchewan, Canada, engineers mine uranium ore that boasts purity levels exceeding 20%. That is roughly 100 times richer than the global average. But extracting it is hazardous. This highly concentrated ore is trapped beneath a thick layer of porous sandstone saturated with water. Dig into it directly, and the entire excavation site will instantly flood. This subterranean diagram shows how engineers bypass the water using artificial ground freezing. They drill deep holes and pump calcium chloride brine, chilled to -30 degrees Celsius, into the soil. The expanding freeze radius turns groundwater into a solid, impenetrable wall of ice. Once the vault is sealed by ice, workers deploy remote-controlled drilling machines to break apart the radioactive rock. Keeping humans out of the immediate extraction zone minimizes their exposure to deadly radiation and protects them from sudden cave-ins. Conquering massive subterranean floods and freezing the Earth solid is an enormous engineering feat. Yet it is merely the brute force prologue to the incredibly delicate chemistry that comes next. You cannot separate atomic isotopes while they remain trapped in solid rock. The mined ore is crushed into a fine powder and dissolved in vats of highly corrosive acid to strip away the physical impurities. Through a series of chemical reactions, the purified uranium is converted into uranium hexafluoride. This creates a highly toxic, exceptionally reactive gas that requires absolute precision to handle without triggering a lethal accident. This gas is then piped into vast, heavily secured facilities filled with thousands of towering, high-speed centrifuges. This animation illustrates the physics inside those spinning towers. As the centrifuge rotates at supersonic speeds, slightly heavier uranium-238 molecules are forcefully thrown outward against the walls. Meanwhile, the lighter, highly reactive uranium-235 gathers in a concentrated stream down the center. Because the weight difference is so small, one spin isn't enough. The gas must be pumped sequentially through a massive cascade of individual centrifuges until it climbs to the 3 to 5% purity required for power. The entire global nuclear power grid relies on this singular mechanical trick, exploiting an almost imperceptible difference in atomic weight by spinning a highly lethal gas at tens of thousands of revolutions per minute. Once the gas finally hits that critical target enrichment, chemists convert it back into a stable, solid powder known as uranium dioxide. High-pressure industrial presses stamp this fine powder into the dense, perfectly shaped pellets we saw earlier. They are then baked inside extreme temperature furnaces for nearly 24 hours to eliminate microscopic air pockets and harden their structure. This diagram shows the final step of containment. Robotic arms stack the hardened pellets into long metal tubes. These rods are forged from zirconium, a unique metal capable of withstanding massive heat, while seamlessly allowing neutrons to pass through to sustain the atomic reaction. The chaotic atomic potential stripped from the Earth and refined in a centrifuge is now tightly secured inside armored rods, fully primed for insertion into the reactor core. Inside heavily fortified nuclear power plants, like the one beneath this massive containment dome, engineers arrange thousands of these fuel rods into a highly precise geometric grid. Once the reactor activates, loose neutrons begin bombarding the uranium-235 atoms, shattering them. This initiates a carefully controlled chain reaction that generates immense heat, instantly boiling water into high-pressure steam. That steam forces massive industrial turbines to spin, generating continuous electricity for millions of homes. But there is a heavy cost to this process. After about a year inside the core, the fuel rods are depleted of their useful energy. They emerge terrifyingly hot and fiercely radioactive. To prevent a catastrophic meltdown, these spent rods are immediately submerged in cooling pools, roughly 30 feet deep. They will sit underwater for over a decade just to allow their ambient temperature and radiation levels to subside, enough to be transferred into these heavy concrete and steel dry casks. The next time you flip a light switch, consider the exact sequence of events required to illuminate your room. That steady current of electricity is the prize humanity extracts by artificially freezing the Earth, spinning lethal gases at supersonic speeds, and shattering matter's fundamental building blocks. It is a precarious, tightly engineered balance between extreme human ingenuity and permanent natural risk.